Yeah, so thanks everyone for joining tonight. Again, this is the second part of our sort of Asian time shifted IGS Global Seminar series to try to accommodate the cryosphere community throughout Asia, who has historically been unable to attend, or like Ralf mentioned, had to wake up at very, very early hours to attend the rest of the IGS Global Seminar series. So this week we have Dr. Ralf Greve from Hokaido University, and he's going to be presenting on the Greenland ice sheet and the impacts of geoengineering in the atmosphere. So without further ado, I will pass it over to Ralf.
Okay, thanks a lot, Dave. And I should say I'm very happy about this opportunity with these Asia-friendly times. Yeah, so it's certainly a practical step towards more diversity and inclusion in our community, isn't it? Okay, so then I'll share my screen. Right. So, no, what's that?
It disappeared, right?
Yeah, no, it's okay.
Yeah, looks good.
All
I don't,
right.
Wait, I don't see it. Did I scroll up? Oh, shit.
Yeah, everything looks good.
I think it's fine.
I don't see a thing, but that maybe my screen is gone. Do you hear me? I hear you, right, Ralf?
Yeah.
We can still hear you and see you. Do you maybe have it minimized somewhere else?
I don't know.
Well,
No.
I can build it up again if you like. I can try to. Oops. Let's see. Now I went out of the screen sharing on purpose. Yeah. So, Ude, can you see me? Can you see the normal Zoom screen now?
Yeah, I can see you.
Okay, then let's try again. Yeah. Okay, screen share.
Yes. Awesome. Thanks.
Now okay?
Yes, yeah.
Ah, great. Everybody else also?
Looks good.
Okay.
Fine.
Great. Okay, then let's get started. So, okay, as Dave mentioned, I'm Ralf Greve from Hokaido University's Institute of Low Temperature Science in Sapporo, Japan. And so today I'm going to present something with a relatively long title. So, reduced mass loss from the Greenland ice sheet under stratospheric aerosol injection and some general considerations about pros and cons of geoengineering techniques. So evidently, this is a bit of a two-part talk. The first half will be based on a study which was published recently. This one here with John Moore as the first author and me as the second, which is about this Greenland ice sheet story. But then, because this is, of course, a very kind of important and controversial topic, I'm also going to say something more in general about geoengineering and which techniques exist and what might be good and what might be bad about it. Also, of course, without going into too much detail, because this would be an endless story, but at least I would like to touch upon the matter a little bit. Okay, so geoengineering, which is also known as climate intervention, so such techniques have been proposed to mitigate the impact of climate warming. And these techniques can be roughly categorized into three different groups, which is A, solar geoengineering, and B, carbon dioxide removal, and C, so-called targeted geoengineering. So I'll come back to these things later in the second part of my talk. But for now, I'd just like to mention geoengineering, which is the attempt to reduce the amount of incoming solar radiation, and by doing so to counteract global warming. And one possibility to do this is the idea of stratospheric aerosol injection, which means, like illustrated in this sketch here, to release a large amount of aerosols, which are typically some sulfate aerosols, to block the amount of incoming sunlight into the troposphere, and by doing so, kind of counteract the amount of global warming. So this idea was the starting point for our study. So what we did was to model the impact of one particular SAI scenario. So SAI is the abbreviation for stratospheric aerosol injection, which is called GeoMIP G4. I'm going to explain this on the next slide. And look on the impact of this particular scenario on the mass loss of the Greenland ice sheet compared to some climate change scenarios without intervention. The background for this was a visiting professorship of John Moore at our university back in late 2019, early 2020. Yeah, that was actually just around the time when Corona started. So we could just finish it before things got really messy. Yeah, and as you see, it took a while to get this study published. It was, I think, in December last year, we finally got the paper published that came out of this study. So it was kind of long-lasting project. Okay, so at least from my perspective, this study grew out of our group's efforts to contribute to the ISMIP6 project. ISMIP6 is the Ice Sheet Model Intercomparison Project for CMIP6, acronym within acronym. So CMIP6 is the Coupled Model Intercomparison Project, phase 6. And the number 6, all refers to the 6th assessment report of the IPCC. So the goals of ISMIP6 were to provide state-of-the-art projections of ice sheet contribution to sea level rise, future sea level rise, along with a quantification of uncertainties. And everything, as I said, as intended to be input for the AR6, the 6th assessment report, which at least this part 1 physical science basis was published in 2029. ISMIP6 is not dead though, so we've been continuing some follow-up projects all along, and it will probably gradually evolve into something called ISMIP7, yeah, it's like towards the next IPCC phase. Now, I should also mention that the ISMIP6 team was actually awarded the IGS Richards Medal in 2023 for its academic and leadership activities in the design and production of future sea level projections. Well, I was not a leading member of this team, but I was at least a contributor, so I share a tiny little bit of the honor. So thanks a lot to IGS. Okay, so what we did for this study was to employ an ISMIP6-like experiment design, but I should stress that this study was not ISMIP6 endorsed. Yeah, I'm just saying this so not to get any wrong impressions that ISMIP6 like may support geoengineering efforts or something like that. So it was just our own brainchild, but the methods were ISMIP6 like. Which means that there is an initialization of, in our case, the Greenland ice sheet until 1990, which is modeler's choice, so no strict protocol. We did a paleoclimatic spin-up approach here, but I'm not going to talk about this here because of time. Yeah, it's published. So from 1990 to 2015, which is the starting time of the ISMIP6 reference period, we bridged this by a historical simulation, which was actually by following an RCP 8.5 scenario. So there was already a bit of mass loss going on of the Greenland ice sheet. But this, again, I'm not going to cover here in detail. And then from 2015 on, the projections start. The ISMIP6 protocol actually calls for projections until 2100. Here we only did it until 2090 for the simple reason that the GCM output, so climate model output, required for this particular geoengineering scenario only covered the period until 2090. Yeah, but otherwise it's ISMIP6 style. So a bit more in detail. So as I said, the model time is from 2050 to 2090 for our projections. We considered 3 different scenarios. The first one is an RCP 8.5, which is a kind of a worst case business as usual scenario. The second one is an RCP 4.5, which is an intermediate scenario. Still not really good. RCP 2.6 would be better, but maybe that's somehow realistic, possible to achieve. And the third one then was this GeoMIP G4 scenario, which is an RCP 4.5 plus an assumption for SAI, stratospheric aerosol insertion, which is particularly releasing 5 megatons SO2 annually over 50 years into the equatorial lower stratosphere, yeah, from 2020 until 2070. And these 5 megatons, this is actually about 1/4 of the total amount of the 1991 Mount Pinatubo eruption. So it's It's quite a lot of stuff, evidently, and it would have to be sustained over 50 years, 5 decades. So this is quite a massive intervention that would be required to do this. So for these scenarios, we had results from 4 Earth system models or global climate models, basically the same. So these 4 here. And so we only did a unidirectional coupling. So we used the climate model results to drive the ice sheet models. Yeah, no real feedback considered. It's a bit simplified, but since the changes are not so dramatic overall in this period, it's probably fine. So which then from these Earth system models, what we require for the ice sheet models is an atmospheric forcing consisting of surface mass balance and surface temperature, and then an oceanic forcing, which consists of prescribed ice sheet retreat masks, which again, I'm not going to explain in all detail here, but it's well documented in the ISMIP 6 papers. And I should also say that these Earth system models do not provide directly the surface mass balance. So to compute that, we had to drive an intermediary model called CEMIC, surface energy and mass balance model of intermediate complexity, which uses the input from the Earth system model to provide the surface mass balance on the grid of the Greenland ice sheet. So this is how the resulting climate forcing looks like. So I'm only showing the atmospheric forcing here. These retreat masks are a bit difficult to visualize, but of course they are also important. So this is the surface mass balance anomaly. So relative to 1961 to 1990 climate, where the Greenland ice sheet was believed to have been approximately in balance. The red curves are the RCP 8.5, the green ones are 4.5, and the blue ones are G4, this SAI scenario. Yeah, the thick line is in all cases the mean of the 4 Earth system models, and the thin lines are the results from the individual Earth system models. And on the right-hand side, it's the same for the surface temperature anomaly. Again, red is 8.5, green is 4.5, and blue is G4. So as expected, that's the order. So RCP 8.5 has evidently the strongest impact, so which means the surface mass balance gets significantly more negative, more melting, and the surface temperature gets significantly more positive. 4.5 is somewhere in between, and G4 is the kind of most, or the least impact of climate change. And I should stress, this is not global. This is only over the Greenland ice sheet, what I'm showing here. Okay, so then, as I said, we use the output from the Earth system models to drive the ice sheet models. And we used 2 ice sheet models for this study, and on purpose 2 quite different ones to kind of see also the impact of the choice of the ice sheet model on the results. And the 2 models specifically are Psychopolis and Elma ice. Well, Psychopolis is uses a finite difference method on a regular grid, 5 kilometer resolution everywhere. The dynamics is a shallow ice shelfy stream hybrid, and thermodynamics is described by an enthalpy method that also takes care of the possibility of temperate ice and water content in the ice. Elma ice, by contrast, uses a finite element method, which goes along with an unstructured mesh. So here are some data, but so the point is it has a higher resolution near the margin in the outlet glaciers and a lower resolution in the interior, while Psychopolis employs a constant 5 kilometer resolution everywhere. So we used the so-called Elma ice sheet setup for this study, which employs shelfy stream dynamics and no thermodynamics. But Elma ice has other options. Yeah, you can go all the way to full Stokes dynamics and also enthalpy thermodynamics. But for this study, we used kind of a simplified setup that has the benefit of reduced computing times. Okay, so this is kind of the important result. So what I'm showing here is the ice volume above flotation counted negatively, so loss positive, and the whole thing converted to an equivalent sea level contribution. The left plot is for Psychopolis, the right plot is for Elma ice. And here it's not relative to a constant climate control one, but it's just the absolute values. So the first thing what we see is if this thin black line, that's the control simulation. It shows that for Psychopolis, the control ice sheet with a constant climate is almost constant. It grows a little bit, while Elma ice has a significant drift in the control one, so towards a growing ice sheet. This is because Elma ice actually did not take part in the ISMIP 6 Greenland exercise. So it hasn't been so carefully tuned for the initial condition. And instead, we used a kind of an off-the-shelf setup for Elma ice. Whereas Psychopolis, which took part in ISMIP 6 Greenland, has been quite carefully tuned for a constant ice sheet in the late 20th century, where the kind of the observed mass balance was also near zero. So it's not at all about model performance. Yeah, it's just a matter of more or less carefully done tuning because of practical reasons. Okay, but then again, like in these climate change plots, this bunch of curves shows the results to the real climate change scenarios, where again the red curves are the RCP 8.5, the green curves are the 4.5, and the blue curves are the G4. Yeah, and again, the thick lines are the 4 Earth system model means, while the thin lines represent the individual results from the Earth system models. And what we can see if we take kind of the difference between the actual projections in the control run is that the results from the 2 ice sheet models are actually quite similar. Not in all details, of course, we will see in the next slide, but no really major differences here, yeah, despite the fact that Elma ice features this model drift over time. Okay, so this now, as I said, this is a more detailed look at the simulated sea level contribution at the end of our model time, so by 2090, and now it's relative to control. So again, left is Psychopolis, right is Elma ice. So these 5 bars are 8.5, 4.5, and G4 scenario. And the 4 colored bars are the 4 individual Earth system models, and this dark gray bar to the right is in all cases the ensemble result. Yeah. So as I said, we can say now Psychopolis and Elma ice are not dramatically different. Yeah, there are a few differences in detail. Maybe most notable that the Psychopolis Psychopolis has kind of a larger difference between G4 and the other non-intervention scenarios than Elma ice. But again, it's not surprising. I mean, it's different models, they have different methods and everything, but it's not dramatically different. So the most important result is, of course, to compare G4 with RCP 4.5. Because just to remind, G4 is actually RCP 4.5, just plus aerosol injection. Yeah, so by comparing these two, we can really directly see the influence of the aerosol injection on the mass loss of the Greenland ice sheet. And in all cases, so if you compare this bunch of results with that one, and same for Elma ice, so what we get is that the difference between G4 or relative to G4.5 is approximately 1/3. Yeah, so here's like this range. And the range is actually about similar if you compare 4.5 to 8.5. Yeah, so kind of the benefit for the ice sheet is kind of G4 relative to 4.5 and 4.5 relative to 8.5 is roughly the same. What these plots also show is the breakdown of the simulated mass loss in surface mass balance contribution and carving contribution. Yeah, so surface mass contribution are the dots in these bars, and carving contribution are the plus signs. Yeah, and here in this breakdown, we actually see a bit of a larger difference between the 2 different ice sheet models. Yeah, such that the carving contribution is quite systematically larger for Psychopolis, while the SMB contribution is larger for Elma ice. Yeah, you see kind of the Elma ice has relatively small carving contribution compared to the surface mass balance part. Yeah, for Psychopolis, it's a bit more balanced. But in either case, for the majority of the results, surface mass balance dominates. Calving is smaller. Yeah, but again, the balance is different between the two models. Okay, now this one shows in a bit more detail the impact on the Greenland ice sheet on look in some map projection. So what we see here is the simulated thickness and mass flux changes again at the end of the model time by 2090. And it's for the ensemble of the Earth system models. So in other words, it's the 4 Earth system model mean in all cases. And it's G4 relative to RCP 4.5. Yeah, so it's the difference of the G4 results compared to the RCP 4.5 results. So in other words, you can say what we see directly here is the gain, the benefit, hopefully, of the Greenland ice sheet from this aerosol injection scenario. So if again the left plots are for Psychopolis and the right plots are for Elmer ice. So for the thickness, it's quite evident. So we see the ice sheet remains thicker, which are the red and red, orange, blue colors all around the ice margin, while in the interior, it doesn't change so much. Yeah, some tendency even towards a slight thinning, G4 relative to G4.5, but it's actually a quadratic scale. It's not linear. Yeah, so it's pretty small. Yeah, but whereas this thickening in relative terms is quite pronounced. Yeah? And it also looks pretty similar when you compare the Psychopolis results and all with the Elmer ice results. Yeah, there's this band of thickening essentially all around the ice margin, while in the interior, the ice sheet does not react very strongly. It's also interesting to look at the mass flux. It's actually the vertically integrated horizontal velocity. Yeah, so that's why the unit is the square of a length per year. Yeah, so it's kilometers per times meter per year. Yeah. So you can also call it, it's the average the depth integrated mean velocity times the ice thickness. That's the same. Yeah. And here now, also blue means slower, red means faster, and of course, so what we hope. Yeah, what should happen is in the same sense as the ice sheet remains thicker, it should accelerate less. So blue colors is good news, red colors, red-orange colors would be bad news. Yeah, so the goal is, of course, that the outlet glaciers accelerate less under G4 than under RCP 4.5. And that's what happens, but related to what I said before, that the dynamic effect is larger for Psychopolis and the surface mass balance effect is larger for Elmer ice. We see this also in the plots here. Yeah? So you see in the Psychopolis plot, yeah, there's much more of these dark blue colors that show a smaller acceleration of the major ice streams and outlet glaciers under G4 compared to RCP 4.5. So for Elmer ice, the effect is also there, but not so pronounced, evidently. Yeah, so this, for instance, this is the Negis Northeast Greenland ice stream with its 3 main outlet glaciers. Yeah, so here we see quite a strong effect in Psychopolis, but only a lesser pronounced effect in Elmer ice. By the way, if you look carefully, you see actually that very close to the ice margin, these orange colors dominate. Again, a bit more pronounced for Elmer ice than for Psychopolis. Now, this would be in principle bad, but that's mainly an effect of the retreat of the ice sheet from the coast. Yeah, so if the ice is gone, of course, there cannot be any ice flow anymore. Yeah, so then it may sound good that there is no ice flow anymore, but it's basically because the ice sheet has retreated. Yeah, so this is kind of an artifact when it comes to interpreting the results. Okay, so this basically concludes the first part of my talk. So let's quickly summarize what we found in this recently published study, namely that, also most importantly, the Greenland ice sheet in our simulations would actually benefit from this SAI, stratospheric aerosol injection scenario. So such that if you compare G4, the intervention scenario with RCP 4.5, the loss of the ice sheet is about roughly 1/3 smaller. So with some uncertainty, of course. So we also compared RCP 4.5 to 8.5, so the intermediate compared to the business as usual scenario, both without any intervention. And in that case, the loss reduction is a bit larger than in this comparison, but kind of similar range. Yeah, a bit like 1/3 to 1/2 approximately. Yeah, so lesson to learn is also, of course, also definitely this is without intervention. Yeah, so evidently climate intervention is not necessary to protect the Greenland ice sheet. Yeah, so a more optimistic climate change scenario can also do the job. But the second part tells us that at least there is a potential that the Greenland ice sheet also benefits from this particular intervention scenario. Okay, on a bit more of a detailed note, we have seen that this partitioning between surface mass balance contribution and calving contribution actually differs quite a bit between the two ice sheet models. So such that calving contributes more for Psychopolis, while surface mass balance contributes more for Elmer ice. And it's in a way not so surprising, because we know very well that calving is all these kind of dynamic changes, in a bit more generally speaking. This is a process that is quite difficult to model. Yeah, so this is still kind of a weak point in the ice sheet models up to date. So it's not so surprising that we see this difference. Yeah, so this is actually something where quite a lot of research is going on, how to kind of improve the description of calving processes in ice sheet models. Okay, but one thing I'd really like to highlight is that this study is by no means intended to be a plea for SAI testing or implementation. So it's research. The purpose is to study and to inform, yeah, but not more. So we keep a neutral stance. It's information for the society. And that already leads over to the second part of my talk, where I would like to look a little bit, not in much detail, evidently, this could be an endless story, but a little bit into the wider scope of the whole problem. So geoengineering in general. So this slide we had before, so we said geoengineering, there are basically 3 types. Solar geoengineering, yeah, trying to reduce the amount of incoming radiation, sunlight. One possibility is stratospheric aerosol injection. So the second possibility that is being discussed quite a lot is this idea of carbon dioxide removal, which means take the carbon dioxide out of the air and put it underground. There are again, there are basically 2 different ideas. The first idea would be this, I think it's usually called direct air capture, which would mean to really take the CO2 directly out of the ambient air, which is a bit tricky because the concentration is still pretty small in absolute terms. Yeah, so we are a bit above 400 ppm now. This is a significant increase in compared to pre-industrial, and it has a pronounced impact on the radiation balance on the Earth, but it's still 0.04%, yeah, which means technologically removing such a relatively small amount of gas is challenging. It's not so easy. The second idea would be to capture it already at the source, which means, for instance, in factories or in power plants that produce quite a lot of that stuff. Now that would have the advantage that you have higher concentrations where you can take it from. Now, if you take it directly from any exhaust gases or factories or something like this. Ultimately, the idea is in both cases to put it underground and store it. Okay, I would just like to give you a bit of a sense for the scale we are talking about here. So the global emissions of CO2 are approximately 40 gigatons per year at the moment. So it's 40 billion tons. If you convert this to liquid CO2, now which is kind of the idea, you pressurize CO2, it becomes liquid, and then you keep it underground. Yeah, it would amount to about 35 cubic kilometers per year of liquid CO2. I compared this to our Mount Fuji, yeah, famous Japanese mountain, which has a volume of approximately 400 cubic kilometers. So which means just in the extreme case of storing the entire current global CO2 emissions underground, that would be equivalent to burying one Mount Fuji every 11.5 years. I would say that's quite a lot, isn't it? Yeah. Now, of course, this is a bit of an unfair comparison because the idea is not to capture everything. The idea is rather to reduce emissions and only capture the amount of unavoidable residual CO2 emissions. But again, just consider the scale. Also, if let's just say for benchmark, we try to capture 10% of the current emissions and maybe could save the other 90%, then we would still talk about something like 3 to 4 cubic kilometers per year. Cubic kilometers, yeah, and already in liquefied form. Yeah, so also 1,000 times compressed compared to the gas volume. This is a lot. Yeah, so you have to keep this somewhere. Cubic kilometers. Yeah, that's a lot of stuff, isn't it? This is big scale. Yeah, I would say it's not so easy to find that much safe storage place for such huge amounts of CO2. So the third part I'd like to talk a little bit about is this idea of targeted geoengineering, which can be summarized under the slogan of local interventions with global implications. So, which means like this solar engineering and CO2 removal, this is more like, by contrast, this is more like really global intervention. Yeah? So it's really a very large scale intervention on the global scale. So by contrast, the idea of these targeted geoengineering techniques would be something really to do something more specific. Yeah, so intervention only at a relatively limited local scale, but still global interventions. So a bit more specifically, focusing on cryospheric topics, yeah, glacial geoengineering. There are some ideas around that mainly focus on the Pine Island freight system of the Antarctic ice sheet, because this is possibly already unstable, or at least on the brink of instability. Yeah, and we know that, let's say, if the West Antarctic ice sheet on the whole becomes unstable, it will produce a multi-meter sea level rise, possibly within a relatively short amount of time, centuries or so. So there are 3 ideas that have been proposed, and here I'm referring specifically to this comment in Nature by Moore and others from the year 2018. So the first one would be to extract or freeze base water at the glacier base, so where it's still grounded, yeah, thus reducing the amount of bases sliding. The second idea that has been around would be to build an artificial island under the floating ice that kind of touches the floating ice, so providing a pinpoint for the ice shelf and resisting ice shelf flow, yeah, which would then hopefully have the benefit of buttressing the upstream glacier and therefore avoiding the amount of mass discharge into the ocean. The third idea is to build an artificial seabed sill or a curtain to block warm water, ocean water, from melting the ice shelf base and thereby stabilizing the whole system. So this third idea has been, I think this has probably got the most attention. This I'd like to have a look a little bit closer. So here is a sketch. This is from this paper by Wolowick and Moore 2018 that came about the same time with this commentary in Nature. So here it's still about a sill. Yeah, so the idea is, as I said before, kind of we have this relatively warm ocean water coming in. That's the floating ice, the ice shelf. This might, for instance, be Thwaites Glacier. And the idea would be that this artificial sill blocks the inflow of warm water into the ice shelf cavity, yeah, so that the base temperature remains quite cold here, and thereby the melt rates under the ice shelf be reduced. So the more recent discussion has changed more away from the sill towards a curtain founded at the seabed and kept in place by some buoyancy elements. So I would say that's probably a bit more of a clever way of doing it, because it's not so extremely resource consuming. Yeah, because building such a sill out of concrete massively, yeah, this would be quite a big scale civil engineering project. Well, that's anyway, but a curtain might be a little bit more of a, let's say, clever custom design solution for this problem. Okay, yeah. Coming slowly towards the end of my talk, I'd like to talk a little bit about general arguments in favor and against geoengineering. So I'm not going to break this down into the individual methods. Or you could say, of course, a lot about kind of the details of these different possible techniques. Yeah, this I'm not going to do. So I'm only going to mention a few more like general pros and cons of the whole topic. So, and it is a highly contentious topic, evidently. Yeah, it gets a lot of discussion in scientific literature and also in the social media and wherever. So the idea is, of course, to use climate intervention, geoengineering tools as a method to mitigate some of the worst aspects of global warming. So I think there is, at least in the scientific community, there is consensus that it cannot replace climate protection measures. Now, this is clear. So just saying, okay, we don't have to protect climate, we do everything by geoengineering, that's of course completely out of the question. Yeah, so the idea is to kind of use it as an auxiliary tool to handle the problem. So such, for instance, this slogan, we won't make it without it. Yeah, meaning that even with our best efforts to protect the climate, realistically, we need additional efforts along these lines of climate intervention to get the whole problem under control. Yeah, for instance, at the most simple thing, we could say it buys us some time. More time for the systemic change required. Offsetting unavoidable greenhouse gas emissions. Yeah, that would especially apply to this idea of CO2 capture and storage. Yeah, so like this idea of, let's say, there is some industry where, like cement production, where global greenhouse gas emissions are just unavoidable with the current technology. And if you really want to go to net zero, we have to deal with these residual emissions somehow. Then, related to this seabed curtain idea, this possibility of perhaps already ongoing or committed West Antarctic marine ice sheet instability. Yeah, this is, if you have to follow the discussion a bit, you're of course aware that this is a very hot topic. Yeah, so I think we can probably agree that the system is at least on the brink of instability. Yeah, whether it's already beyond the tipping point or not is controversial, but we're dangerously close, at least. This is kind of clear. So let's say this seabed curtain idea might be a way to get at least some safety from this particular threat, which could really lead to same kind of multi-meter sea level rise in a relatively short amount of time. Okay, however, so a big problem is, of course, that any of these geoengineering techniques might serve as an excuse to tackle the root cause of the problem, delay tackling the root cause of the problem, which is this much more systemic change of reducing greenhouse gas emissions, carbon-free society, and other greenhouse gases, by the way. It's not only about CO2, yeah, methane, yeah, also a relatively big player. So I think, at least in the scientific community, I think, of course, we would agree that that's a bad path. Yeah, so as I said before, kind of the idea is rather to use it as auxiliary tools. But, well, there are, of course, players around who might not think that way and who might take it as an excuse to say, well, okay, we have geoengineering, so why should we protect the climate? We can handle the problem on that level. Yeah, so dangerous. Another problem is side effects. So we're dealing with an incredibly complex system here, and I think we have to agree or accept as scientists that despite our best efforts, we will never be able to understand the climate system perfectly. Yeah, we can kind of asymptotically improve. That's our effort. Yeah, increase our understanding, learn more, get a better grip on the system. But I think coming to the point where you can really run a climate model and 100% rely on the results, for instance, the response to any sort of geoengineering intervention, it's not realistic. We can certainly anticipate a good deal of positive and negative effects, but not necessarily all of them. There might be bad surprises. Well, there might also be good surprises. Yeah, it's not everything is necessarily bad, but the bad ones are, of course, the riskier ones. So there may be some side effects. What to do with them? Yeah, might be extremely expensive to then counteract the side effects. Another argument is the issue of resources. Yeah, so the problem is in a world of unlimited resources, it might be maybe not so problematic to do both, yeah, climate protection and climate intervention, geoengineering. But in real life, of course, resources are limited. There's only so much work time, money, energy, logistics available for everything. Yeah, so there's also some danger that maybe too intensive, massive scale geoengineering efforts may draw away important resources where they're needed more. Yeah, this part, yeah, kind of tackling the systemic change that is really needed. So as we see, it's a complex problem. Yeah, there is not a simple answer to it. Shall we do it or not? It's difficult to say. So my personal stance, and I should really stress it's my own one, yeah, not of the co-authors of the study I was talking about will probably take by this 100%. But I have to say that overall, I'm fairly skeptical about the whole thing. Yeah, also from a very general consideration. I mean, let's say technology brought us to the brink of climate disaster. And now the idea is even more technology is supposed to fix it. I'm quite skeptical whether this is really the right approach. There is a famous quotation from Albert Einstein, which I've actually always liked a lot, stating that we cannot solve our problems with the same thinking we used when we created them. And these big techno fixes to a technological problem would be exactly that, yeah, kind of the same thinking. So I'm on this very general level, I'm kind of skeptical whether it will work overall, even if in detail the interventions might work. But if you consider the whole complexity of the kind of coupled climate, society, economical system, difficult. But I should also stress that I'm not at all against doing further research into the matter. So on the previous slide, we had these pros and cons. Yeah, so it's a difficult problem. And these ideas for climate intervention, geoengineering techniques, they're out anyway. So I think despite the fact that what I said, I'm basically skeptical about the whole thing. I think it's still a good idea to try to understand potential implications about these methods. Because be it only because it will be done anyway. Yeah, so if we as a scientific community don't do it, the corporate world will certainly do it. Yeah, I think the oil companies or energy companies, insurance companies, they have an interest in these things. But if we leave it only to the corporate world, it will happen in the hiding. Yeah, if the scientific community also deals with it, then at least it's in the open. Yeah, so I think this is definitely a strong point for at least continuing the research into the matter. Yeah, I said before, we will never understand everything, but that doesn't mean that we understand nothing, of course. Yeah, so we can still try to understand as much as possible what might happen if we do this and that. Well, as I said, my personal stance, you might agree or disagree, partly disagree, happy to discuss. Okay, that's all I have to say. So thanks a lot for your attention and interest. I have also collected the references, and the talk will be published on YouTube as usual, and I'm also going to put the slides on Zenodo. So you will, especially if you're interested in the references, it will be accessible. Yeah, I will make the slides available as PDF on Zenodo. Okay, so yet again, thanks a lot.
Excellent. Thanks, Ralf. That was a great talk. That was really thought-provoking at the end there. I enjoyed that. Yeah, we've got some applause there. That's great. I'll open it up for questions. If anyone has any questions for Rolf or would like to share their own view on any potential geoengineering interventions, I'll open it up.
So, yeah, I have no idea about geoengineering, but how do you actually model the aerosol input? How do you put that into Secopolis?
Well, not directly. It happens on the level of the climate model. So this is the climate models deal with them. Yeah, so this is these 4 climate models. Yeah, they're all capable of handling these additional aerosols in the atmosphere. So that on that level it happens. Yeah, so it goes into the climate model as an additional forcing of the climate system. And as a result, we get these surface mass balance and surface temperature forcings. That's how it works.
Yeah, do you want to spell these climate models out for us?
Oh my goodness.
Like BM.
Okay, yeah, okay. ESM is Earth System Model in all cases, yeah. Or Earth here, just ES. So BNU is Beijing Normal University. So that's the model from the university where John Moore used to work.
Okay.
I don't remember the detailed meanings of all these abbreviations, but HGM is the British model. Hadley, yeah,
okay.
Yeah, Hadley and so on. And MIROC is the Japanese model from the University of Tokyo. Yeah, which they use a lot for these assessment report simulations. Yeah. And chem, there's 2 flavors of MIROC. This chem means chemical, so this has a more refined chemistry module attached to it.
Okay.
Yeah, so that's these 4 models, and we chose them simply on the basis of availability because these were the models that had these scenarios. Yeah, so without the geoengineering, of course, yeah, you would have the whole range of ISMIP 6 models available, but only a few of them contributed in this GeoMIP, yeah, like geoengineering model intercomparison project exercise. So that's why we had only a relatively limited range of models that we could use for the whole comparison.
So then the Earth system models must somehow change the atmospheric fluxes or whatnot based on like this first.
Yeah, I mean, everything. I mean, I mean, they can handle these aerosols. Yeah, so that's how it works. So you just put additional aerosols in the stratosphere and let the model deal with it. The radiation balance changes evidently, yeah, and so on. Yeah.
Okay. All right. Thanks. Yeah. Okay. So you can do atmospheric simulations.
Yeah, not personally me. So this was done mainly by the Chinese group of John Moore. So
Yeah.
So Chao Yu and Li and Zhao, they mainly did these climate models, also guided by John Moore.
Yes. Now we just had the word this morning on how we could make simulated atmospheres, but for a totally different purpose, based on Calypso observations, whatever. But yes. Interesting. Well, at least it provides an understandable framework of how you would even evaluate these types of aerosol injections.
Yeah.
Yeah, I'm not a fan, like personally, I think it's like worse than how do you use the devil to drive out the Beelzebub?
I mean, that's what I mean. A techno fix for techno problem. Yeah, I mean, if you look at the scale, it's kind of mind-boggling. Yeah, like one quarter of a massive volcanic eruption every year over 50 years. Yeah, I mean, and the point is, as you know, from the natural experiment. Yeah, if you stop it, the climate changes back to normal within a few years. Yeah, like that's what happened after such volcanic eruptions. Maybe 2 years, 3 years, it gets colder and then it's back to normal. So if this is not sustained over the whole period, then everything goes down the river again. Yeah, then it's worth nothing. Yeah.
Right.
But that's one of these kind of ideas of this targeted geoengineering, to kind of have a little bit of a smaller scale. Yeah, so it's still easier to set up a several, don't know, tens or 100-kilometer long seabed curtain than doing something like that. Yeah, or also this CO2 storage. Yeah? I mean, this is kind of, also, frankly speaking, I find this insane. Yeah, cubic kilometers. Yeah, every year. Where on earth do you want to store all that stuff? And does anybody want to live near such an underground deposit? Just imagine you have some tectonic process and it comes up again. Yeah, this is absolutely, yeah, thousands or people will die. Yeah, it produces a lake. Yeah, it's heavier than air. Yeah, so there have been natural disasters where CO2 was released from lakes or so. Yeah, and kind of covering nearby villages. Yeah, so you just die quickly. Yeah, this is
right.
Okay, you could try to put it under the sea. The German government recently said like that, okay, we look into it, but only under the sea, not under land. Yeah, but okay, then maybe you don't have this problem that it may kill a lot of people, but it makes also the whole thing more expensive. Yeah, because then you have to drill it you have to bury it under the sea, not just under land. Yeah? Another aspect is that CO2 has a critical temperature of, I think, 32 degrees, which means if you put it underground where it's warm, yeah, it won't even stay liquid. It will be a supercritical fluid, yeah, which is even less prone to stay in place than a real liquid.
So on the data side, Ralf, we are looking at, so there is atmospheric LiDAR observations, right? There have been atmospheric sensors which have been available for 20 years, like CloudSat Calypso, and the detection algorithms applied to these LiDAR data cannot even capture thin aerosols, such as suppose you have a Pinatubo or eruption or a wildfire. So then these aerosols stay in the atmosphere for years, and they wrap around the globe, and they actually have quite the effect on solar radiation. So now we are working on an algorithm to actually identify these types of really thin aerosols, which are escaping the current data detection schedule, which means like the databases for how much carbon flux do the natural catastrophes change, or how much insulation flux, like what's the role of how do you quantify even the role of all these aerosols, isn't totally solved on the data analysis side. So we have a whole grant from NASA to improve the detection algorithms for 20 years back. And then you modelers can like rerun this or whatever. But then, I mean, you'd have a better database to compare what's even the effect of putting X amount of junk in natural, technically, in addition to what's already happening from volcanic eruptions, wildfires, all these other catastrophes, because you want to make sure you have all these boxes covered.
Yeah, it makes sense, of course. And the better you understand the system, the safer you can make predictions of these interventions, of course.
Roland, I'll pass it over to you.
Thank you. Just prompted first to digress to what Uta was just describing. I was yesterday evening at a presentation on wildfires, and the main speaker there pointed out that the last few years of global forest fires have actually led people to realize that there's new stratospheric chemistry that they didn't even know about now that so much extra material has been lofted up high, and apparently even the possibility of doing the good work of mending that ozone hole. So in terms of things we don't know about, there's a lot of other sources of aerosols that perhaps even less benign than what Ralf was talking about. what I actually stuck my hand up to comment on was, of course, that these sort of approaches to fixing the global temperature by altering the radiation balance don't do anything about the other nasty effects of CO2, such as ocean acidification.
Yeah, of course. I mean, it's clear. I mean, this is, you cannot fix everything. This is clear. I mean, it's, as I said, it's only, let's say, at least by informed people, I think it's absolutely clear. It can only be an auxiliary tool. Yeah, as I said, mitigate some of the worst, yeah, not all. This is clear. I mean, you cannot fix everything by these methods. Yeah, the idea is rather maybe to have an auxiliary tool in the toolbox on top of systemic change, reducing greenhouse gas emissions and so on. That's clear. I mean, no geoengineering tools will be able to offset all problems.
Yeah, I just mean that there are other issues of what might be politely referred to as carbon pollution besides the global heating aspect.
Yeah, perfectly right. I agree. The better solution is, tackling the real problem. Yeah, definitely.
Like you said, though, there could be stakeholders, so to speak, which would just say, okay, fine, we're not even trying for the difference between 8.5 and 4.5, which would have a bigger impact, right? We can still perhaps avoid 8.5 altogether, because, I mean, when ISMIP was set up, it was kind of a catastrophic prediction. And so then people would go, oh, guess we're done. We can like happily keep polluting. And so the amount of politicians you could see say that is definitely out there.
I mean, maybe not only the real hardcore guys may say it openly, but it may kind of creep into heads, at least as some background thinking. So well, we know maybe we don't have to try so hard because we have these techno fixes. It doesn't have to be 100% this or that, but it can also be a gradual thing. But I think, knowing the real world a bit, I think this would happen to some extent, at least. How much, I don't know, but to some extent, certainly. I mean, this is how the world works. This systemic change is extremely painful. I mean, it's not easy, evidently. We have to change our whole lifestyle. This is difficult. And if there is this idea around to fix it somehow by kind of easier methods, it's a dangerous path, I think. Also, I'm really skeptical whether overall it will do anything good.
Yeah. Anything else? We've got the last minute or two here for a question, if there's anything else. If not, I will thank you all.
I could toss in one last point, perhaps, on this general discussion of geoengineering. As Ralf pointed out, the issue of I think what he called it, targeted interventions for the global implications with regard to preventing ice sheet changes. I think there's another interesting comparison between that and the atmospheric injection, which is that presumably, essentially, everybody on the planet would benefit from reductions in global air temperature. Whereas one could argue that interventions addressing ice sheet discharge primarily affect people who, which is a lot of people who live near the ocean.
Yeah, exactly.
Not going to do anything for the ski resorts.
That's true. I mean, it's again the same story. Like Ute said, any particular measure will only be a partial solution. It never can tackle the whole spectrum of problems. This is clear. But I mean, I think, of course, also reducing sea level rise is certainly not such a bad thing to do. Even if not everybody benefits from it. But as you say, I mean, there are quite a few people who live near the coast and would benefit from less sea level rise. So.
Yeah.
And you have to
Interesting,
make sure.
interesting topic. Thanks for the presentation, Rolf. I think you've got everyone's brains spinning on hyperdrive now. It's good. So thanks very much, Rolf. That was a great talk. Thanks to all of you who joined. As per usual, this was recorded and will be posted on the IGS YouTube page. I just quickly wanted to plug next week. We have 3 interesting talks from a group of early career scientists. I will just quickly share my screen and plug these 3 talks that are taking place next week during the regular IGS time. I also wanted to note that the next time-shifted seminar will take place on March 27th and 28th, depending on which part of the world you're in, but it'll start at 2 a.m. GMT on Thursday, March 28th. So we've got 3 more weeks or 4 more weeks until that, or 3 more weeks. Sorry, yeah, 3 weeks. And one of those presentations is going to be from Xian Hua from Taiwan, who's going to be giving an introduction to Arctic research taking place in Taiwan, and Yifan Wang, who is going to do a presentation on some remote sensing work of the Greenland ice sheet. So sort of a little observation-based studies of the Greenland ice sheet. And again, that'll take place on March 28th. So thanks again to everyone. Thanks, Ralf. I hope you all have a good day or a good night wherever you are. And I look forward to seeing you at another IGS seminar.
Okay, thanks a lot. Bye-bye.
Bye, everyone.
See you.
Thank you, Ralf. Great
Yep.
talk. Thank you very
Thank
much.
you. Thanks.